in the few of our previous lectures, we have done few results and a few questions related to the topic of a Fourier transform. And today, let us continue with the same topic, Fourier transform. And a very important question related to the topic of Fourier transform is there. We have a function f of x, and the function f of x is defined like this: a minus modulus of x, and modulus of x is less than a, and the value is 0 if the modulus of x is greater than a. In the first part, you need to find out the Fourier transform of this function, and in the second part, you need to uh, prove that integral 0 to infinity sine t upon t whole square dt is equal to pi by 2. This will be the second part, and we shall also prove in the second part integral 0 to infinity sine t upon t whole power 4 dt is equal to pi by 3. We shall prove these two deductions in the second part. So let us start our question. We have to find out the Fourier transform of f of x, and by the formula, Fourier transform of f of x is minus infinity to infinity f of x e raised to power iota s x dx. This is the formula for Fourier transform. We have studied this formula earlier. It is actually the complex form of a Fourier transform. We have to use this formula for finding out the Fourier transform of f of x. This is e raised to power iota sx into d of x. Now, as you know, you just see the interval is there. The interval we have, this is minus a is less x a greater than a, or x is less than minus a. This is the meaning of these two intervals. Now it means we can split the integral into three integrals. The first integral is minus infinity to minus a, and minus infinity to minus a is this interval, minus infinity to minus a. And what is the value in this? That is 0 into e raised to power iota sx dx, plus the second interval will be minus a to a, and this one. And in this interval, the value of the function is a minus x of modulus into e raised to power iota sx dx. And the next interval will be a to infinity. And this is the interval we have. And in this interval, the value is 0 again. So 0 into e raised to power iota sx dx. Ultimately, the first integral and the last integral is 0, and we shall get the value from the second integral, and we shall integrate it. So for integrating it, we need to use some extension. E raised to power iota sx is cos of sx plus iota sine of sx dx. So this is by Euler formula, and if we see this function, and you have to write down the terms as two integrals. a minus x of modulus into cos of sx dx plus minus in a to a minus x of modulus into sine of sx dx. Now, if we see what will be f of minus x, that will be a minus of x modulus, and that will be same as a minus x modulus, and that is f of x. It means f of x is the even function we have, and this is even, cos is already even, so we can use this formula, that it will be twice of integral 0 to a minus x of modulus into cos of sx dx. And in this integral, this is a even function, this is odd function. So in the case of even into odd, we will get as odd function. And in the case of odd function, the formula will give us zero value. So now you can integrate this integral. For integrating this, you will write down the values. X modulus is the same as x. So it can be written like this. Now you can integrate it by parts. This is first function, this will be second function. And the first function as it is integral of cos, so that is sine sx upon s within the limits 0 to a. Outside there is 2 minus integral derivative of a minus x is minus 1. And again we will integrate it sine sx over s dx. So you just now to substitute the limits, and when you substitute upper limit a here, a minus a will give you 0, and when you substitute lower limit 0 here, sine of 0 will always give you 0. It means the first value will vanish, and that will be minus and minus plus. So ultimately again the integral of sine is come out to be minus of cos sx upon 1 extra s will be there. So you can write down minus cos of sx upon s square will become here 0 to a. Now you can substitute the limits. For upper limit a, you will get cos of as, for lower limit 0, cos 0 is 1. So it can be adjusted. You can take a minus sign inside. We will write down the term like this. So ultimately, now you can use the formula of cos 2a, and it will give you, that is 2 sine square as upon 2. So we 2 sine square as upon 2 will be there. This will be the output of the value, and you can combine this. That will be 4 upon s square sine square as upon 2. So this is the ultimate value of the Fourier transform. Sorry, Fourier transform of f of x. And by inverse formula, you can find out the value of the second part by using inversion formula. Now you want to evaluate a second part. In the second part, we have to find out the values of two integrals. So for computing this, we shall use inversion formula. So by inversion formula, we shall have f of x, that is 1 upon 2 pi, integration is minus infinity to infinity, e raised to power minus iota sx into f of s d of s. And we shall use the values now. 1 upon 2 pi minus infinity to infinity. And this is your value of f of s. It has already been written. This is the Fourier transform. Now you can use this value, that is 4 upon s square sine square as upon 2 e raised to power minus of iota sx ds. And what will come out to be after a simple computations, it can be written like this, that will be 2 upon pi, that is minus infinity to infinity, that will be sine square as upon 2 divided by s square e raised to power minus of iota sx ds. Now, as we know, we want to compute this. That is 0 to infinity and sine t upon t whole square dt. We want to compute the value of this term. What we have f of x. Uh, like that, we have the term that is sine square as upon t. But what we require sine square t. You see the numerator. So it means we should have this value should be as t. So it means you should use the value, or you can substitute, put a is equal to 2, so that this 2 will be cancelled with this. Ultimately you will get sine square s, and that is sine square s upon s square. I think it will work. And you shall use x is equal to 0, x is equal to 0, therefore f of 0 is equal to 2 upon 5, and that will be minus infinity to infinity minus infinity to infinity. That will be minus infinity to infinity. I am repeating again. We are going to use a is equal to 2 and x is equal to 0, and what will come out to be f of 0, that is 2 upon pi minus infinity to infinity. This will be sine square t upon t e raised to power x will be 0, then e raised to power minus of 0 will give you 1, and that will be d of s. And okay, we have the parameter s, not t. So you will write down the expression at this moment in terms of s only. So that will be sine square s upon s square. So now let us compute that. It can be written, that is minus infinity to infinity sine of s upon s whole square d of s, that will be pi by 2 into f of 0. This 2 over pi will be taken to the left hand side. And now, what will be the value of f of 0? You will compute the value of f of 0 from the given function, that is a minus x of modulus, when x mod is less than a, and that is 0 when x mod is greater than a. You know that the value 0 x equal to 0 will lie in this interval. And what will be that this interval, that is minus a less than x less than a. And on the real line, if you draw a real line minus a to a, and the value 0 will lie on this line. Suppose this point is x equal to 0, and at x equal to 0, we shall use the value of function as a minus 0 of modulus. So a f of 0 will be a minus 0 of modulus, and you will get a, that is pi by 2 into a. And on the left hand side, sine of s is upon s. It is an even function. It is here sine s upon s is even function, because at s equal to 0, it will give 0 over 0 form, and if it will give 0 over 0 form by L hospital rule, the denominator will be 1 and numerator will be cos of s. And you know that cos s upon 1 will give you cos of s, and cos of s is always an even function. So if it is even, so you can use this formula, that is the sine s upon s whole square d of s. So ultimately, uh, we shall write down what it come out to be 0 to infinity sine s upon s whole square ds, and this 2 will be taken to this side, it will give you 1 by 2, and this is pi by 2. And what is the value of a we have used? And that value is used as 2, and 1 2 will be cancelled, so you will get the value as pi by 2. So this is your required value of the first part of second. This one, this value should be pi by 2. This is we have proved. No doubt, you can change the variable here. This is the integral in terms of parameter s. You can change s to t. Okay, let us compute the other part of a second. That is, we have to compute 0 to infinity. That is sine t upon t whole power of 4 into dt is equal to pi by t. We have to prove that this value is equal to pi by t. The value should be pi by t. This is we want to prove now. And for proving this, we shall use a Parseval identity. So by Parseval's identity, and what we should have 1 upon 2 pi minus infinity to infinity, that is f of s whole square into ds minus infinity to infinity f of x modulus square into d of x. This is the extension of a Parseval identity, and we shall use it. That is 1 upon 2 pi minus infinity to infinity, and the value of f of s is 4 sine square as upon 2 upon s square. And because here is a square, so you will take square here into ds, and we know that in the interval minus of infinity to infinity, we have the defined value, and which is non-zero. That is, the value is a minus x modulus, and this value is for the interval minus a to b. And for other intervals, we have zero value of f of x. So you can use the values, and the second part that will be adjusted over here. 4 square will give you 60. Will give you 16 upon 2 pi integral minus infinity to infinity is there, and that will be written as sine as upon 2 upon s can be adjusted, and this square term will be taken to the power. So ultimately it will be power over ds, and on the other side of that, because it is the even function, so you will use the property of even function, that is 2 times 0 to a, that is a minus x whole square, as we already know that this is the even function, and now you can integrate it a minus x whole cube into 3 into minus 1, and you will use the limits, and when you will substitute the limits over here, for the upper limit a, it will give you 0, and because a minus a will be 0, and for the lower limit 0, it will give you minus a cube. So ultimately you will have 2a cube upon 3. And now you can take sum of the terms from the left hand side to the right hand side. So minus infinity to infinity sine of as upon 2 upon s whole raised to power 4 into ds, that is 2a cube upon 3 into this 2 will be cancelled with the 16, and you will have pi over 8. So this is the value we have, and what will be the value, and that is 2 can be cancelled with this 2 also, you will have 4 over here. Now you can use the value of e cube. We already know that a is used as 2, so if you use a as 2 on the right hand side, you shall use a as 2 on the left hand side also. So just write down in the next step. So ultimately what we should have, we shall use the value of a as 2 here. So using a is equal to 2, we will have minus infinity to infinity, that will be sine s upon s whole part over d of s, and now you can use this as 2 into pi upon 3 into 8, and you will have 2 into 8 will be 16 pi upon 3 into 8. Now this 8 will cancel with this, so ultimately you will have 2 pi upon 3 on the right hand side, and we already know that sine s over s is even function, and we have used this property in the first part also. So that is it. That will give you 2 times 0 to infinity sine of s over s whole power 4 d of s, that is 2 pi upon 3, and now this 2 will be cancelled with this 2, and we can write down the expression like this: 0 to infinity sine t upon t whole power 4. I am going to change the variable, because in definite integral change of variable doesn't make any difference, so that value is pi by 3. So this is the required value of the uh, second part. So this proves the required result, and it is a very important part the question how to prove a deduction. So you must be aware of this, that how to find out the Fourier transform of a function of x and how to find out the deductions related to that function. Now, let us continue with that. We should have the relationship between Laplace transform and Fourier transform. Now, is the small result. We have a relationship between Fourier and Laplace transforms. But both are transforms. We have a function if f of t and the function is e raised to power minus st into gt, and this is the function defined for t greater than 0. The value is 0. For t less than 0, then this is the relation which we want to prove. Then Fourier transform of f of t is equal to Laplace transform of g of t. This is we want to prove, and this is a very important result. Now, let us prove. As we know by definition that Fourier transform of f of t is minus infinity to infinity, and that will be e raised to power iota st into f of t into dt. Now, this integral can be splitted into two integrals, minus infinity to 0 and 0 to infinity, e raised to power iota st. So, first of all, let us see the value of the integral. Now, you see, this is the interval we have, and this interval will be minus infinity to 0, and this interval will be 0 to infinity. So, minus infinity to 0 interval will give you 0 value of the function. So you will use 0 as the value of the function f of t. And for the second integral, that is 0 to infinity, e raised to power iota st into e raised to power minus s of t into gt dt. This is the value of f of t. Now, this integral will vanish because it will give you 0 value, and in the second integral we should have e raised to power, uh, the value will be there, that value will be e raised to power iota s minus s into t into g of t dt. We are using the value. Now, you see what is the function here, that is e raised to power iota s into iota s minus s into t is there. If we use, you just see, you can adjust the terms like this. 0 to infinity is there. You can change the variable also. This is e raised to power iota st, e raised to power minus s of t is there. Suppose I change the variable over here, and it can be written like this, because what we are using the value of the function. Uh, this is the function we have. It can be written minus is common, s is common, and 1 minus iota is there into e into g of t into dt. This is the constant value, this one. So you can use here, put e s into 1 minus iota, or you can say that that will be s minus s iota as a parameter p, that will be 0 to infinity e raised to power minus pt into g of t into dt. I shall use this value as another parameter p. Obviously, it will have some value, and that value is equal to small. And if we remember the definition of Laplace transform, then Laplace transform of f of t should be 0 to infinity e raised to power minus st into f of t dt. And the change of parameter can also exist. Now, if we compare this integral with this integral, what we have? The variable is there, no doubt about that. In place of f, we have g, and in place of s, we have p. So, ultimately, what we can have? This is the value of the Laplace transform, or the definition of Laplace transform is there. So, by the definition, we can use that is the Laplace of g of t. Now, I think it's clear now that Fourier transform of f of t is equal to Laplace transform of g of t. So this is the small result which we can use whenever we require this. So I conclude here. We shall continue in the next class with some of more results related to the application part of Fourier transform. We shall continue that how to solve a differential equation with the help of a Fourier transform, specifically a partial differential equation. So thank you very much. Thank you.